Memory. It's one of the most fascinating and, let's be honest, complex phenomena in all of neuroscience. We all wish we had a little more of it, right? But how does it actually work? Today, we're going to pull back the curtain and explore the incredible architecture of this vital cognitive circuit. We're going to look at how our brains literally build the very stories of our lives.
All right, here's our roadmap. We'll kick things off with the three fundamental processes that are behind every single memory you have. Then, we'll look at the classic time-based way of classifying memory and see how that compares to the more modern function-based model. After that, we'll do a deep dive into the two major types of memory before finally mapping this entire amazing system onto the physical structures of the brain.
So, first things first, before we get into all the different types and locations, we have to understand the foundation. It doesn't matter if you're remembering a phone number you just heard or your first day of school, every single memory is governed by three core processes.
It all begins with encoding. You can think of this as registration. It's the initial learning, the moment the information first enters your brain. Next up is consolidation, which is all about storage. This is the process of taking that information and maintaining it over time. And finally, you have retrieval, which is exactly what it sounds like, the ability to access and recall that stored information when you need it. So remember those three: encoding, consolidation, and retrieval. They are the universal pathway for every memory we create.
Okay, so historically, neuroscientists classified memory based on a really simple metric: time. How long could the brain hold on to a piece of information? This gave us a pretty straightforward three-tiered model that's actually still quite useful for getting our heads around the basics.
So first, you've got immediate memory. This is also called working memory, and it lasts just seconds. Think about repeating a phone number someone just told you. That's your prefrontal cortex in action, holding it just long enough to use it, no real storage necessary. Next is short-term memory. This can stick around for hours or maybe even a couple of days, like remembering what you had for breakfast. This process requires some initial storage in a structure called the hippocampus. And finally, we have long-term memory. This is the big one. This is when information gets transferred to the neocortex for permanent storage, and it can last for years or even a lifetime. Now, what's really key here is that even though the storage locations are different, that prefrontal cortex acts like the conductor of the orchestra, coordinating the retrieval process for all of them.
Now, here's where it gets really interesting. Our brains are constantly deciding what's actually worth keeping. For example, you can probably remember this morning's breakfast, right? That's a short-term memory sitting in your hippocampus. But let me ask you this. What did you have for breakfast on November 4th of last year? Almost nobody can answer that. Why? Because for most of us, it was just another breakfast. It was deemed unimportant, so it was never consolidated into long-term storage. The only person who can answer that question is someone for whom that day was incredibly significant. Maybe it was their birthday or their anniversary. It was an event so important that it got flagged for transfer to the neocortex.
And that very distinction between an important event and an unimportant one leads us directly to the modern model of memory. See, today, neuroscientists don't really classify memory by how long it lasts, but by the mode of retrieval. Specifically, it all comes down to whether or not retrieving it requires conscious effort.
This new way of thinking splits memory into two major categories. On one side, we have explicit or declarative memory. This is all the stuff you consciously know and can declare, facts, events, stories. On the other side is implicit or non-declarative memory. This is the knowledge that you express unconsciously through your performance, like skills and habits.
Let's dig into that first category, explicit memory. This is the memory of what? All the facts, the figures, and the personal stories that make up our conscious knowledge base.
Now, explicit memory itself has two subtypes. The first is what we call episodic memory. This is essentially your autobiographical memory, the story of your life. It's totally time and context-based. It captures specific episodes, where you were, when it happened, and crucially, how you felt about it.
This type of memory is uniquely fragile, a fact that's tragically illustrated by Alzheimer's disease. Just imagine a father in the early stages. He can recall his son's best friend of 30 years perfectly. That's a solid, secure long-term memory. But when that friend visits with his new wife, who the father just met last week at their wedding, he has absolutely no memory of her, or even the wedding itself. That specific episode was never consolidated. And this happens because episodic memory is critically dependent on the hippocampus, which is one of the very first brain regions to be ravaged by the disease.
The second type of explicit memory is semantic memory. If episodic memory is your life story, semantic memory is your internal encyclopedia. It's a massive database of facts, concepts, and general knowledge about the world. Things like knowing the capital of France is Paris or that water boils at 100 degrees Celsius. This knowledge is stored across the brain's association areas and is remarkably resilient, often staying largely intact even well into the later stages of Alzheimer's.
Okay, let's shift gears now to the other side of the coin, implicit memory. This isn't about remembering what anymore. Now we're talking about remembering how. These are the memories that guide our actions, often completely without our conscious awareness. Implicit memory has 4 key subtypes. First is procedural memory. This is muscle memory, acquired skills like driving a car or riding a bike, which are managed by the basal ganglia and cerebellum. Second is priming. This is where being exposed to something influences how you respond later. For instance, you'll recognize the word doctor much faster if you've just seen the word nurse. That's a function of the neocortex. Third is associative memory, which creates those conditioned emotional responses, and that's governed by the amygdala. And finally, there's non-associative memory, which is just simple habituation to things in our environment, a process handled by our basic reflex pathways.
So we've covered the fundamental processes in the modern ways we classify memory. Let's move into our final section, where we get to put it all together. Here, we're going to map these abstract functions onto the actual physical circuitry of the brain and see where all these processes really live.
Okay, so let's take a tour. The frontal lobe, specifically that prefrontal cortex we mentioned, serves as the executive center. It's the king of retrieval for all memory types. The temporal lobe, which is home to the hippocampus, is the critical hub for forging new episodic memories. The vast association areas spread across the parietal, occipital, and temporal lobes act as the huge distributed storehouse for all our semantic knowledge. And finally, the subcortex, which includes the basal ganglia, cerebellum, and amygdala. That's the domain of all our implicit unconscious memories.
For our episodic memory specifically, consolidation relies on this incredible neuroanatomical loop known as the Pays circuit. This pathway is how a memory gets properly processed and strengthened. Information flows from the hippocampus to the mammillary body, then up to the thalamus. From there, it travels to the cingulate gyrus, loops through the parahippocampal gyrus, and then passes through the entorhinal cortex right before returning to the hippocampus. This reverberating circuit is the physical mechanism that builds our personal memories over time.
Now, a key player in this circuit, maybe the most important player, is the entorhinal cortex. It's often called the gateway of memory, and for good reason. This structure acts as a critical filter. It's basically assessing the importance of every experience, deciding if it's significant enough to be fully consolidated by the hippocampus, and maybe even nominated for permanent storage up in the neocortex. You can literally think of it as the brain's bouncer, deciding which memories are important enough to get into the club.
Let's watch this whole process in action with a real-world example. Imagine you're learning the formula for a plus b squared in algebra class. On day 1, it's just a simple short-term memory, easy enough to pull from the hippocampus for a quiz. But if you never use it again, it's just going to fade away. However, if you apply it again and again, solving dozens of problems, the entorhinal cortex senses its recurring importance. It says, hey, this is important, and flags it. That triggers its transfer from the hippocampus up to the neocortex, transforming a fleeting fact into permanent, expert-level knowledge.
So here's the crucial takeaway. Our memories are not passive recordings of the past. They are actively built, curated, and filtered by a physical circuit in our brains. And that leaves us with a pretty fascinating final thought to ponder. If this gateway, this entorhinal cortex, is filtering our entire lives based on what it perceives as important, what truly makes an experience worth saving? And maybe more to the point, what are we telling our brains to remember every day?